Hello, sir. Dr. Patnaik, sir.
Yes, yes, yes. Can you hear me? Hello?
Yes, sir.
Can you hear me?
Yes, it is audible.
Okay, okay.
So we'll start sharp at 6 p.m.
Yeah, yeah, yes, yes, yes.
Recording in progress.
Sir, can you share the screen, sir? Dr. Patak, sir, if possible, can you share the screen?
Is it visible now?
Yes, sir.
Now, is it visible?
Yes, sir. The screen is showing, sir. So
Okay,
you have a mail open.
okay.
Sir, can we start, sir?
Yes.
Okay. So good evening, everyone. A warm welcome to the second day of our faculty development program organized by R&D Cell of Regent Education and Research Foundation group of institutions. Our FD program on Green Horizon, okay, and we are delighted to have with us Dr. Satyajit Patnaik, sir. Okay. Dr. Satyajit Patnaik, sir, is postdoctoral research associate from Luleå University of Technology, Sweden, who will deliver a talk on virtualizing bioenergy, advances in biomass systems using digital twins. Dr. Patnaik is an engineering professional with extensive experience in thermochemical energy systems, process design, and carbon capture technologies. He holds a PhD in mechanical engineering from NIT Mizoram and has over a decade of academic and industrial experience. Currently, he is a postdoctoral research associate at Luleå University of Technology, Sweden, leading research on digital twins and machine learning for carbon capture systems. He has developed and delivered courses on renewable energy and thermal systems, supervised student research, and contributed to international projects. His areas of expertise include sustainability, ESG frameworks, techno-economic analysis, and life assessment and life cycle assessment. So we are thankful to have with us Dr. Satyajit Patnaik, sir. And sir, can we start, sir?
Yes. Thank you for introducing me, and also thank you for the Regent Education Institution for inviting me for this Total 6 days virtual faculty development program. So everyone, good afternoon, everyone. My name is Dr. Satyajit Patnaik, and I am a postdoctoral researcher at the Department of Civil, Environmental and Natural Resource Engineering. Today, I will be talking about virtualizing bioenergy, interdisciplinary advances in biomass systems using digital twins. So the core idea is that bioenergy, which plays a crucial role in renewable systems, can become smarter, more efficient, and more sustainable through digital twin technologies. Over the next 90 minutes, I will be explore what this means, why it matters, and how it is being applied in real systems or real world. So here is the roadmap for today's lecture. So I will be begin with some background on the energy transition, then move into fundamentals of digital twins. After that, we will discuss the bioenergy systems and reasons why virtualization is particularly useful for them. The middle section of the talk will focus on interdisciplinary advances. This means I will look at contribution from engineering, computer science, environmental science, and economics. Towards the end, I will go through specific case studies, examine benefits and challenges, and finally look ahead at future direction. And I will have plenty of time for questions at the end. So the global energy transition demand has been steadily rising over the last few decades, and this trend is expected to continue while efficiency gains have
Sorry to interrupt, sir.
Yeah.
Sir, the presentation is not visible on the screen.
Not visible?
Yes, sir. The email ID is been shown, but the presentation is not shared, sir.
Now it is
Yes,
came.
it is now. Yes, sir. Yes, sir. Thank you, sir.
Now it is changing. You can check it is. This is second slide. Slide is changing. Have you seen?
Yes, sir.
Okay. Okay. So global energy demand has been steadily rising over the last few decades, and this trend is expected to continue. While efficiency gains have slowed down the growth a bit due to population growth and industrialization, especially in developing economies, are driving demand higher. So at the same time, climate change poses a major challenge. We know that energy is responsible for a large share of global greenhouse gas emissions. That means the way we meet this rising demand will determine whether or not we succeed in reaching our climate goals. Energy security is another important issue that fossil fuel supply chains are vulnerable to geopolitical shocks, as we have seen in recent years. All of this creates pressure to diversify our energy portfolio and increase renewable capacity. And then global energy transition too. So the renewables are rising rapidly. Solar and wind are the fastest growing. You can see this map. And hydro remains significant, and bioenergy has a steady role. But despite this growth, fossil fuels still dominate. Coal, oil, and natural gas provide the bulk global primary energy. Governments have set ambitious targets. Many countries have pledged to achieve net zero emission by 2050 or later. But achieving those commitments requires not just deploying renewables, but also ensuring that they work reliably together in the energy mix. This is where bioenergy is special. It is renewable, but unlike solar or wind, it is dispatchable. That means it can provide energy whenever needed, making it a stabilizing force in the grid. So in the global energy transition 3, we can see looking ahead, we need an energy system that is resilient, sustainable, and flexible. And bioenergy contributes to that because it's renewables and storable. It can complement variable renewables like solar and wind. However, integrating bioenergy into a modern energy system is not a trivial. Feedstock vary, its supply chains are complex, and the efficiency of conversion process is not always optimal. This is why advanced approaches is like digital twins are needed. They can help us manage that complexity and turn bioenergy into a smarter, more predictable resources. So now the role of bioenergy, the bioenergy is actually the largest single contributor within renewables today. It accounts for more than half of renewables energy used globally. So, however, it is also incredible versatile. Biomass can be used for electricity generation, for heating, for producing transport fuel, and for making bio-based chemicals. This versatility is what makes it central to the idea of a bio-based circular economy. By turning reduces and waste streams into energy, bioenergy closes loop, reduces landfills use, and lowers emissions from waste burning. That's why so many governments and research initiatives continue to support it. And for the bioenergy too, the role of bioenergy too, the looking to the future, bioenergy holds even greater potential, and sustainable biomass use can support rural economics by creating new markets for residues and byproducts. It can also enable decentralized energy systems. For example, small biogas plants that serve a community or a farm. This kind of distributed energy generation increases resilience, especially in areas where not well connected to the grid. But to unlock this potential, we need smarter ways of managing variability and uncertainty. So this is exactly where digital twins comes in. So to help operation optimize and predict outcomes. So why virtualization is matters? So why do you need virtualization for bioenergy? The answer lies in complexity. Biomass is not like a coal or natural gas. It is highly variable. Its moisture content, composition, and energy density, the change depending on where it comes from and how it is stored, depending on geographical area and weather conditions. These all things are effect on this biomass. So the supply chain is also complex and subject to disruption. For example, bad weather can reduce harvest residues or make transport more expensive. Without real-time optimization, plants risk efficiency or even failure. Digital twins allow us to run virtual model of our bioenergy system that update continuously with sensor data. That means we can forecast outcomes, adjust operations proactively, and reduces risk. In other words, they turn uncertainty into manageable information. So what is digital twin? So we start by defining what a digital twin actually is. At its core, a digital twin is a digital replica of a physical system. It's not just a static model, it is a dynamic system that continuously updates with data from the real world. Think of this way, in the past, we built simulation models that could predict how a boiler or digester behaves under certain conditions. But those models quickly became updated because they did not account for real-time changes. But a digital twin solves that problem by integrating real-time data streams with simulation. So in bioenergy, a digital twin of a biogas plant might continuously receive data about feedstock composition, digester temperature, or gas output. And this allows operation to not only monitor but also predict future performance. So this diagram, you can see this diagram shows how digital twins works. So on the left, we have the physical system. It could be a biomass power plant or a biogas digester or a supply chain. Okay, sensor such as those measuring temperature, moisture or gas composition. So this data will be collected and send it through a pipeline, often via using IoT, Internet of Things, and cloud platforms. So that data feeds into a digital twin model, which is combination of physical simulation and AI or machine learning models. So the twin generates forecast and insights, which operators can then use to take corrective or proactive action in the real system. The key point is the feedstock loop is the physical and digitally continuously inform each other. So this creates a living model that is always aligned with reality. So in this slide, it is showing the hybrid modeling in digital twin. So now if the digital twin is only as good as the model behind it. Traditionally, engineers relied on the first principle models. So I can say you next slide what is first principles models. That is equation based on physics and chemistry. These are the robust out, but often computationally expensive and limited in handling uncertainty. On the other hand, data-driven machine learning models are powerful at recognizing patterns, but sometimes act as a black boxes. The best solution is hybrid approach by combining the strength of physical-based simulation with data-driven methods. So we create models that are both interpretable and adaptable. So for bioenergy case, this is especially important because biomass properties is varying so much. So hybrid models can capture these variations while still being grounded in scientific principle. So now how hybrid models support is bioenergy systems. So we need to, so how to hybrid models help bioenergy, especially first, they can handle feedstock variability. You can imagine the receiving a batch of biomass with higher than the expected moisture content is there. So physics models might predict the drying requirements, while machine learning models can forecast how that will affect energy yield. And secondly, hybrid models improve real-time optimization. By combining sensor data with simulations, they allow operators to make decisions that are both accurate and fast. Finally, they enhance predictive control. That means not just reacting to issue, but anticipating them. Whether it is a risk of digester instability or a boiler efficiency drop, this predictive capability is what makes digital twins powerful tools for bioenergy plants or systems. So different industry across industries use of digital twin. So digital twins are not a new idea. They have been applied in several industries with a great success. In aerospace, for example, every modern jet engine has a digital twin that monitors its health and predicts maintenance needs. So in healthcare also, digital twins are being developed for patients using data from wearables doctors can simulate and personalize treatment. In manufacturing, factories use digital twins to optimize through throughput throughout and reduce downtime. The takeaway here is that the concept is proven, but we are not reinventing the wheel, but rather adapting a powerful idea to the specific challenges of bioenergy. So digital twins across industries too. In this slide, in the energy sector, we already see digital twins being used in wind turbines and electrical grids. For example, wind farms use digital twins to predict turbine failures before they happen, reducing downtime. So utilities use them to simulate grid behavior under different loads. These applications show that digital twins are versatile and scalable. If they can handle something as complex as national power grid, then they can also be applied to bioenergy plants and supply chains. The lesson is that bioenergy can leverage existing experience while tailoring solution to its unique challenge. So relevance to energy systems. Why we are digital twins particularly relevant to energy systems? Because energy systems are dynamic and interconnected. You have fluctuating supply, variable demand, and a need for high reliability. Digital twins allow us to model that complexity and make smarter decisions. For bioenergy, this relevance is even greater. Feedstock supply is variable, conversion processes are sensitive, and integration with the grid requirements precise forecasting. Digital twins provide the predictive capability to balance all these moving parts. In short, we can say they make bioenergy more competitive and more compatible with other renewables. So now we need to know about the different type of biomass feedstocks. That bioenergy system themselves, starting with feedstocks, that is agriculture residues are one of the most common sources. This includes rice husk, wheat straw, corn straw, sugarcane bagasse, and these residues are often underutilized, and in some regions they are burned in the open, and for this cause air pollution. By diverting them into energy systems, we can turn a problem into resources. However, the challenge is variability. So moisture content can change depending on weather. Ash content varies with the soil type, and calorific value, which is important parameter, is differs by crop and harvest. This heterogeneity makes it difficult to design one size fits all conversion systems. Again, this is why virtual models are so useful. They allow us to simulate different scenarios and adjust operation accordingly. And biomass feedstocks too. The beyond agriculture residue, another important category of biomass feedstock is forestry and industrial byproducts. Forestry residue include wood chips, sawdust, and bark. These are often abundant in countries with strong timber industries. Industrial byproduct like baggage from sugar mills or black liquor from paper mills also provide significant biomass potential. Instead of being discarded or underutilized, they can be turned into energy, adding value to existing industries. Another is municipal solid waste is another contributor, especially is organic fraction. Using it for energy not only generates power but also reduces landfill burden and methane emission. The challenge again is variability, that moisture content in sawdust differs from that in municipal waste, and each requires different conversion strategy. So digital twins help us understand these differences and adapt operations accordingly. The biomass feedstock 3, we can say in this the emerging feedstock like algae and aquatic biomass represent existing frontiers. Algae, for example, grow rapidly, capture CO2 efficiently, and can be cultivated in non-arable land or wastewater. This makes them highly sustainable. However, harvesting and processing algae is expensive and energy intensive. Similarly, other aquatic biomass sources show promise, but come with logistical and technical hurdles. This emerging feedstock highlight why virtualization is so important. We can use digital twins to simulate growth rates, harvesting schedules, and conversion efficiency before scaling up production. That reduces risk and accelerates the path from lab experiments to commercial viability. So whether we are talking about residues, byproducts, or algae, digital twins give us the flexibility to model diverse feedstocks and optimize how they are used. So conversion pathways, like number 1 is that thermochemical. So bioenergy conversion can be broadly divided into thermochemical, biochemical routes. So thermochemical pathways include processes like combustion, pyrolysis, and gasification. Combustion is the oldest and most straightforward, simply burning biomass for heat or power. And pyrolysis, on the other hand, is a process where biomass is heated without oxygen, producing biooil, syngas, and char. And for gasification, uses limited amount of oxygen or steam to convert biomass into syngas, which can then be used for power or fuels. The advantage of the thermochemical routes is their efficiency and scalability. You can build a large plants that provide reliable outputs, but the downside is that they often require high temperature, significant infrastructure, and are sensitive to feedstock variability. This is where digital twins can really help by simulating these complex reactions and guiding operators in real time. So conversion pathways and biochemical process. It is the second major category, this biochemical conversion. The most common methods here are anaerobic digestion and fermentation. So anaerobic digestion uses microorganisms to break down organic matter in the absence of oxygen, producing biogas, mainly methane and CO2. And fermentation, meanwhile, is used to produce bioethanol from sugar and starch rich from the starch rich crops. Biochemical processes are generally more environmentally friendly because they operate at lower temperature and can use wet biomass without drying, but they are slower and more sensitive. For example, digester microbes can be easily stressed by changes in pH factor, then temperature or feedstock composition. Now, here it is digital twins can be game changers. How it is? By monitoring microbial activity and simulating outcomes. They can help stabilize process and improve yields. Now, in the third one is this conversion pathway, the integrated biorefinery. The future of bioenergy is not a single output plant, but in integrated biorefineries, it is there. So these are facilities that use a mixed technologies to produce multiple products like electricity, heat, fuels, and high value chemicals. Think of it like a petroleum refinery, but for biomass. Instead of just burning biomass for power, a biorefinery can extract chemicals, ferment sugars, generate heat, and capture syngas. So all of those things are in one system. Obviously, that level of integration brings huge complexity. Different processes interact, and optimizing one may reduce efficiency in another. That's why virtualization is so critical. So digital twins allow us to model the whole system, test scenario, and find the best balance of outputs. What are the current challenges now? So despite the potential, bioenergy faces several challenges. You can see first feedstock variability. No two batches or biomass are exactly the same. Second thing is supply chain complexity, like collection, transport, and storage can be expensive and logistically difficult. And third one, like process efficiency, many technologies still struggle to reach the performance and cost levels of fossil fuels. And finally, environmental sustainability. Not all biomass is automatically green. We need to ensure that land use, biodiversity, and carbon footprints are properly considered. So these challenges highlight why virtualization is not just a nice to have, but a necessity. It allows us to manage uncertainty, improve efficiency, and make bioenergy more sustainable. So, why virtualizing biomass? So, first, monitoring biomass properties like moisture or ash content, it will be fluctuate. Virtual models help us track those changes in real time. Second thing, optimization. By simulating different operational strategy, we can identify the best set points for reactors or digesters, leading to higher efficiency. And third one is reliability. Digital twins allow us to anticipate problems before they cause downtime. This predictive capability can save both time and money in industrial operations. And now, why virtualizing the biomass? Another criteria is another reason to virtualize that integration with the larger energy system. Bioenergy does not operate in isolation. It needs to interact with the grid, with markets, and with other renewables. Digital twins make that integration possible. For instance, they can forecast how much energy a plant will produce tomorrow based on expected feedstock deliveries and current conditions. So that forecast can then inform grid operators or market bids. So virtualization helps bioenergy move from being a stand-alone plant to being an active player in a smart, interconnected energy network. So digital twin architecture, we need to know about how it is worked. So you can see the architecture of the digital twin in bioenergy. On the left side, we have the physical asset that may be reactors, boiler, digesters, and even the supply chain. These are equipped with sensor that capture data like temperature, gas flow, or feedstock moisture, and that data flows into acquisition system. Often though through SCADA or IoT platforms, the core of the twin is a combination of models, physics-based, data-driven, or hybrid. On top of that, we have optimized and control algorithm, control signals algorithms also is there. Then turn raw data into actionable insights. So finally, those insights are translated into control signals that adjust actuators, set points, or maintenance schedule in the physical plant. The cycle repeats continuously, creating a closed loop between the real and virtualization system. So in digital twin architecture, the data loop is that heart of the digital twin. The physical system sends data to the twin. Then the twins run simulations and predictions, and then sends recommendations back to the physical systems. What makes the powerful is that it is not one way. The twin continuously recalibrates itself based on new data, which keeps the model accurate over time. That's big difference from traditional simulation, which often drift away from reality as conditions change. So this means a biogas plant can continuously learn and improve its operation as more data is collected. It's like having a living learning model running alongside the plant. In the case of digital twin architecture for the people and process, we should also remember that the digital twins are not just about technology. They are also about people and process. Operators need user-friendly dashboards to interpret insights. Maintenance teams need workflows that incorporate prediction from the digital twin. And management needs governance structure to ensure cyber security and data integrity. We can say, in other words, like a successful digital twin is not just a technical tool, but part of an organizational ecosystem. If people don't trust or understand the outputs, the twin won't deliver its full value. So human factors and institutional design are just as important as sensor and algorithms. So here you can see the data and IoT in the biomass. So data is the lifeblood of digital twins, I already said, and IoT sensor are how we collect it. In biomass systems, we monitor parameters like feedstock moisture, reactor temperature, pH, and gas composition. Each of these variables can make the difference between stable operation and costly failure. Edge computing is becoming important here. Instead of sending all raw data to the cloud, we can process some of it locally at the plant site. That reduces latency and ensures faster responses, which is critical when conditions change rapidly. The cloud still plays a role, especially for storing large data sets and running heavy analytics. The combination of edge and cloud gives us flexibility and resilience. Together, they enable the real-time responsiveness that makes digital twin effective. Now, data and IoT in biomass but just utilizing sensor is not enough. So we also need to think about interoperability and data quality. If one sensor speaks a proprietary protocol and another uses an open standard, they might not talk to each other easily. That's why standardization is crucial. Data also has to be validated and clean. Biomass systems often operate in dusty, wet, or corrosive environment, which can affect sensor reliability. If bad data enters in the twin, the prediction will be wrong. Finally, we can say that we must address cyber security. As plants become more connected, they also become more vulnerable to cyber attacks. So protecting data streams is essential, not just for plant safety, but for broader energy security. So interdisciplinary advances in engineering. So engineering plays a central role in making digital twins for bioenergy. Engineers develop process models for combustion, gasification, and digestion. But in computational fluid dynamics, or we can say CFD, help us understand how gases and solids flow inside the reactor. Engineers also optimize plant design. For example, where to place heat exchangers and or how to size, how much size of digester. Then scaling up is another challenge. Designing a lab system is one thing, but making it work in industrial scale is much harder. So digital twin act as a bridge between lab results and industry reality. So reducing the risk of scale up and improving overall plant design. So digital twin is a act like that. So in the case of computer science, so computer science contributes through artificial intelligence, machine learning, and IoT integration. These fields provides the algorithms and infrastructure that allows digital twins to process and learn from data. For instance, machine learning can predict reactor performance or detect uh, anomalies before they become serious. IoT platforms handle the massive flow of sensor data, and data engineers ensure that everything is stored, processed, and visualized properly. The challenge is making sure these systems are reliable, scalable, and secure. Bioenergy plants can generate gigabytes of data every day. Without robust computer science tools, it would be impossible to turn that data into actionable insights. In the case of environmental science, that brings another critical perspective. We can't just optimize bioenergy for efficiency. We also need to ensure it is sustainable. So life cycle assessment or LCA allows us to evaluate environmental impacts across the whole value chain. Digital twins can integrate the life cycle assessment data in real time. For example, they can estimate the carbon footprint of producing a batch of biogas, considering both feedstock, sourcing, and conversion. This allows operators to make environmentally conscious decisions while still optimizing for performance. So economics and policy provide the enabling environment. Like techno-economic analysis tells us whether a bioenergy project is viable. Policy incentives such as subsidies or carbon credits determine whether plants are financially attractive or not. So digital twins can help here too. By simulating scenario, they allow us to test different market or policy conditions. For example, how does a change in feed in tariffs affect plant profitability, or what happens if carbon tax is introduced? So ultimately, digital twins can support decision making not only at the plant level but also at the policy level by providing transparent, data-driven insights. So process simulations tools. Traditional simulation tools have laid the groundwork for digital twins. Aspen Plus, you heard about that. Aspen Plus is one of the most widely used. It models chemical process in great detail, making it ideal for simulating gasification or pyrolysis. COMSOL multiphysics is another powerful tool useful for modeling heat transfer, fluid flow, and even microbial process. The limitation of these tools is that they are often static. They don't automatically update with real-time data, but they are still incredibly valuable as the physics-based backbone of a digital twin. By integrating these with live sensor data, we can move from offline simulation to living adaptive models. So another process simulation tools like MATLAB or Simulink, which is excellent for control system design, and Homer, that is which is widely used for simulating renewable energy systems and microgrids. These tools let us explore how bioenergy integrates with other renewables at the system level. Co-simulation is becoming increasingly important. That means linking different simulation environments together. For example, coupling a biochemical process model in COMSOL with an energy system model in HOMER. So this gives us a holistic view of both plant level process and system level interaction. So digital twins build on this by adding the real-time layer, making sure the models stay relevant and accurate as conditions change. So have your AI and ML approaches in the bioenergy systems. The artificial intelligence and machine learning are the heart of modern digital twins. And these techniques allow us to extract patterns and make predictions from massive amounts of data. For instance, neural network can predict how a digester will respond to new feedstock mix or forecast biogas yield based on past performance. Anomaly detection algorithm can identify unusual behavior like a sudden drop in methane output before operators even notice. So reinforcement learning goes one step further. Like it does not just predict; it learns strategies by trial and error. So, for example, it can continuously adjust feeding rates and in a digester to maximum gas yield while avoiding instability. So the beauty of artificial intelligence is that it adopts as more data is collected. Over time, the model becomes smarter, just like an experienced operator who learns from years of practice, but at much faster pace. So in the hybrid models, it is a powerful as AI. It also has limitation. Purely data-driven models can be black boxes. They may predict outcomes, but they don't always explain why those outcomes occurred. That's where hybrid models come in. So a hybrid model combines physics-based simulation with machine learning. The physics ensure that model remains grounded in scientific principle, while the artificial intelligence adds adaptability and responsiveness. So in bioenergy, this is especially important. For example, a gasification model based only on physics equation might not capture subtle variation in biomass feedstock. But a machine learning model trained on historical plant data, they can. So together they produce a model that is both accurate and interpretable. So in practice, hybrid models provide the reliability of engineering with the flexibility of AI, a best of both worlds approach. So here it is, the different type of first principle method and data-driven approach. In first principle method, you can see you can use the differential equations, multi-physics simulation, process simulation, then statistical analysis. In machine learning, so this slide categorizes the modeling simulation technique that support digital twins in bioenergy. On the left side, we have mechanistic or first principle approaches. This includes differential equation, multi-physics simulation, and process simulation. And differential equation are the foundation. They described how mass, energy, and momentum change over time. Tools like MATLAB, Python, or even Fortran have been used for decades to solve this equation. Then we have multiphysics simulation. This captured more complex interactions such as fluid flow, heat transfer, and chemical reaction happening at the same time. COMSOL, ANSYS Fluent, and OpenFOAM are common platforms here. These are the essential, especially important for detailed reactor modeling. So process simulation package such as Aspen Plus, Aspen HYSYS, and DWSIM allows us to model entire conversion pathways from feedstock input to energy and byproduct outputs. They provide the big picture of plant level operation. On the right side, we have the data-driven approach. The statistical methods such as design, experiments, and response surface methodology are used to identify the most influential factors and optimize condition. These time series analysis and Monte Carlo simulation also fall in this category. So finally, machine learning adds another layer of capability. Techniques like neural networks, support vector machine, decision trees, and random forest can we find patterns in large amounts of data. These methods excel at handling noisy, variable feedstock data and predicting plant performance in real time. So we can say together these techniques from the toolbox of digital twins. So the most effective approach is usually hybrid, combining mechanistic models with data-driven techniques, giving us both scientific grounding and adaptive learning. So here is the limitation of first principle models in bioenergy. It's worth highlighting why digital twins are such a step forward. Traditional first principle models, those based purely on physics and chemistry, have important limitation in bioenergy. First, they are expensive and time-consuming to build, especially for complex multi-step process like digestion or pyrolysis. Second, they often required many iteration and sensitivity analysis to account for variability. So third one, they are not always designed for optimization. Most were developed as offline engineering tools. And finally, biomass conversion processes are highly nonlinear. So a small change in moisture or pH can have a large or unpredictable effects. So these non-linearities are difficult to capture with equation alone. So that's why integrating machine learning and real-time data is essential. So it overcomes the rigidity of purely theoretical models. So proposed methodology for digital twins using simulation, data, ML combined approach. So this slide shows how simulation, data, and machine learning can be combined into a unified methodology for digital twin in bioenergy. At the core, we have simulation that could be process simulation like Aspen Plus for gasification or biochemical models for an aerobic digestion. They provide the physics-based backbone of the twin. On the top of that, we integrate machine learning, generative learning techniques such as neural networks or GAN can create scenario and optimize feedstock or operating conditions. Perspective learning, like reinforcement learning, can recommend control action, for example, adjusting feed rates or set points in real time. So the key is the feedback loop, like real-time sensor data from the plant flows into the model. which continuously update the refines itself. This makes the twin a living system, not just a static model. So the benefits are clear: improved process stability, higher conversion efficiency, and greater energy yield, all while reducing cost. So this methodology illustrates how we move from theory to practice by combining physics, data, and AI into one coherent digital framework. So how do we move beyond these limitations? So one way is through a common optimization methodology that combines machine learning with simulation. So in bioenergy, this could mean using process simulation as the backbone, while machine learning models handle variability in feedstock properties. An optimization algorithm then search for the best operating strategies. So for example, we can simulate a gasifier with a different feedstock, use machine learning to refine prediction, and then run optimization algorithm to maximize efficiency while minimizing emission and cost. So the result is powerful toolkit that helps both researcher and industry operators design better plants and run them more efficiently. This is essence of digital twin methodology for bioenergy. So let us put this context with the case studies. A virtual biogas plant. So imagine we have a digester treating agriculture residue. Normally, operators rely on rules of thumb or basic monitoring, checking pH, gas yield, or temperature. But with a digital twin, we have a live replica of the plant running in parallel. So if a batch of feedstock comes with high nitrogen content, the twin can simulate how this will be affect microbial activity, methane yield, and the risk of ammonia inhibition. So operators can then adjust the mix of dilution rate before the problem occurs. So this means higher stability, less downtime, and more consistent biogas production. In some research trials, methane yields has increased by 10 to 15% through digital twin optimization. That's also a huge gain for plant economics. So in the case of optimization, the optimization is where digital twins really shine. By continuously analyzing feedstock quality and process parameters, the twin can recommend the ideal operating strategy. For example, it might suggest mixing feedstocks with different carbon to nitrogen ratio to maintain microbial balance. Or it might adjust hydraulic retention time to maximize methane output. What's powerful here is the prediction. Instead of waiting for problems like pH crashes to occur. So the twin once operates in advance. So this proactive management transforms how biogas plants are run from reactive to predictive operation. Then biomass supply chain optimization. In this case, digital twins are not limited to the plant. So they can also apply to the entire biomass supply chain, collection, transport, storage. All of these add cost and uncertainty. So a supply chain twin can simulate different collection routes, evaluate storage options, and even factor in weather impacts. For example, if heavy rains are expected, the twin can recommend an alternative storage strategy to prevent feedstock spoilage. So by doing this, operators can cut cost, reduce waste, and ensure a more reliable feedstock supply. So considering that logistics can represent up to 50% of total bioenergy cost. Optimizing the supply chain is just as important as optimizing the conversion process. So in the case of predictive maintenance in biorefinery, so another it is a powerful application is predictive maintenance. So bioenergy plants rely on complex equipment, boilers, turbines, pumps, and digesters. So unexpected breakdowns can be extremely costly. So digital twin allows us to monitor equipment health in real time. By comparing actual performance to the digital model, they can detect early signs of wear or failure. For instance, a subtle change in vibration patterns might indicate that a turbine bearing needs attention. Instead of reacting to failures, operators can schedule maintenance proactively. So this reduces downtime, extends equipment life, and saves money. Some industries have reported maintenance cost reduction of 20 to 30% when using digital twin based approach. So what are the benefits of this virtualization? So before we dive into the challenge, it's important to pause and highlight the benefits this in the virtualization bioenergy system. So first, we can say the efficiency. So by continuously optimizing operation, digital twins can increase energy yield. For example, improving methane production in biogas plants or maximizing syngas quality in gasifier. Second thing is sustainability. So with better process control, emission can be reduced, waste minimized, and environmental impacts tracked in real time. So this allows operators to meet both economic and environmental goals. And third one is cost reduction. Predictive maintenance avoids unplanned downtime, while supply chain optimization reduces feedstock cost. These savings directly improve plant profitability. Finally, in the decision support, digital twins don't just provide a raw data, they deliver actionable insights. They can help plant operators, engineers, and policymakers make better, faster decisions. So now the challenges and limitation. While digital twins offer enormous promise, we also need to be realistic about the challenges. The first major issue is data. So bioenergy plants often don't have consistent or high quality data streams. Sensor can be failed, readings can be drift, and sometimes key variables are not measured at all. So without reliable data, the twin can't function properly. Okay, another challenge is computational demand. High fidelity simulation, especially when combined with real-time learning, can require significant processing power. Smaller operators may find the infrastructure cost daunting. And integration with Legacy system is also tricky. Many bioenergy plants were built years ago with older control systems that don't easily connect to modern IoT platforms. So in the retrofitting them requires both money and technical expertise. So these are the challenges, and another challenges are there. So beyond the technical side, there are also policy and human challenges. Like regulations are not yet adapted to digital twin technologies. For instance, who is responsible if an automated twin makes faulty recommendation? There are also skill gaps. Successful deployment requires knowledge in engineering, data science, computer science, and environmental assessment. So few organizations have all these skills in house. So finally, we can say the cybersecurity is also growing concern. As plants become more connected, they become potential targets for cyber attacks. Protecting critical infrastructure like energy system is not optional, it is necessity. So these challenges don't mean we should abandon digital twins. They mean we must approach them thoughtfully. So, future research we can say from this bioenergy virtualization, we have to looking forward. So I see we see several exciting research directions. One is self AI-driven self-optimizing plant. Imagine a biogas plant that not only monitor and predicts but also autonomously adjusts its own operations to maximize yield. So another direction is integration with smart cities and smart grids. Digital twins of bioenergy plants could be linked with digital twins of buildings, transportation, and utilities to create a coordinate energy ecosystem. So standardization will also be critical. Right now, each digital twin is often built as a custom project. So developing common data protocols and frameworks will make twins more interoperable and scalable. So these are areas where academia, industry, and governments need to work together to accelerate this bioenergy virtualization progress. So in the case of policy and industrial adoption pathway, so for digital twins in bioenergy to truly take off, supportive policy frameworks are essential. Governments can help by funding pilot projects, setting standards, and offering incentives for digitalization. So industry also has a role to play. Collaboration across the value chain is necessary. Equipment infrastructure manufacturer, equipment manufacturer, software developers, and plant operators all need to work together. And academia can support by training the next generation of experts who can bridge engineering, computer science, and environmental knowledge. Ultimately, we can say adoption depend on showing clear value, whether it is higher efficiency, lower cost, reduce emission. If digital twins can demonstrate these benefits, industry will embed them. So to conclude, let me summarize the key takeaways. The bioenergy is a vital part of the renewables energy transition. So digital twins provide a way to unlock its full potential by managing variability, improving efficiency, and ensuring sustainability. Success requires an interdisciplinary approach combining engineering, computer science, environmental science, and economics. While challenges remain especially in data, competition, and policy. So the opportunity are enormous. The future is one where bioenergy systems are not just physical plants, but intelligent, adaptive, and interconnected virtual physical ecosystem. So thank you for attention. I would now like to open the floor to discussion, and I encourage you to ask not only about the technical aspects, but also about the broader implication for policy, sustainability, and society. Thank you.
Thank you, Dr. Patnaik, sir.
Thank you so much, sir.
Thank you.
We'll now open the floor for a brief question and answer session. So participants, if you have any question, you can please ask. Participants can unmute or can write in the chat box. We'll get to the question and ask Dr. Patnaik, sir. So there's a question from
Is there a question?
so there's a question from Suganya. The question is, sir, is there possibility of petrol blend biofuel to be available in India like biobunk?
Yes. It's already, nowadays is going to, the ethanol is blended with petrol, some percentage is already available in India.
Another question is from Dr. G. Tirupati Naidu.
What is the cost of unit by biomass plant? Actually, it is depending on the what is means how much you need the product, means output, depending on the output. Okay, so it is I can't say because it is I'm not a manufacturer of the biomass plant, so I can't say it is. So depending on the plant size or everything. Okay.
Any more questions from the participants?
Sir, I have a question. Thank you for this session. Like, this is a very new thing to me, and like very great. Like, it's a great thing to know. I have a question that is, what you are what you have said about what was here in the content of this thing, that is
Can you
bioenergy.
repeat question again? Actually, some questions, some words are not here.
Okay. Sir, the thing is, what is my question is, this thing is in the in a research level, right? So this
Yes.
has very less real life operation. So like what is the barrier? Like what is stopping us to get into the real life operation?
No, I understand. See, in the bioenergy sector, obviously it is new, but in digital twin, if I talking about the other manufacturing sector like aerospace, any other like Siemens, if I talking about Siemens, is a very big company. Already they are using digital twin, but in the bioenergy sector, obviously they are not using. So that's why we are doing the research level. So and even CO2 capturing, any other process also is totally new, not physically adopted any company still now research based research process is going on. And another thing also, if I talking about in India,
Yes, sir.
suppose in thermal plant, okay,
Yes,
coal
sir.
thermal plant or everything. Similarly, they are if I talking about NTPC are using coal with some percentage of biomass, okay,
Hmm.
in the thermal
Yes,
plant.
sir.
So they are continuously thinking about the adaptability of biomass after some years, okay.
Hmm.
So that's why I already said that it is very difficult to this digital twin adoption some, because it's the IoT, the very big this sensitive sensor will be there. So in the old setup, it is very difficult to set up new technology in the old setup. So it
Okay.
is very
Okay, sir.
requirements more much costing also issues is there.
Okay, sir. Sir, one more question, that is, I am from chemistry background. I have a MSc in chemistry. So how I can like incorporate myself in this thing, or how I can
Uh,
how I can get into this research, or how what would be my contribution to this thing, like how I
uh,
can start, or
yes. You can start. So first of all, you need to learn. You know about chemistry, so obviously you know the biomass characteristics, how the gas compositions, everything you know. So
yes, sir.
now you need to learn the AI, artificial intelligence, and whatever
Okay.
the some simulation software. Like in the chemistry case, in the Aspen Plus is the very good software. So you learn these things.
So
And
what
another
is the
software
software?
is
Can you repeat? What is the software name?
Aspen Plus. So it is
Aspen Plus.
actually licensed version. So
Hmm.
if you want to use in open source, so software name is DWC. I'm writing in the message
Yes, sir. It would be very
DWC.
good, like helpful.
So this software is open source
Okay.
software. So you can download it and you can try it.
Okay, sir. Okay. Thank you. Thank you, sir.
Sir, there are more questions in the chat box.
Ah,
Nirmala Bhattacharya has asked, is the biomass plant and biopower plant the same or not?
is the biomass plant or bioplant is same or not? Yeah. Biomass, biomass is same. See, some biomass plant or biopower plant, what about that bioenergy? Ultimately, this produces the energy. So that energy we can say maybe is a chemical form or maybe the power form. Okay, maybe it is heat energy also. They can produce heat energy. It is also is we can say it is the bioenergy plant.
Okay, sir. So there's another question from Shorojit Roy. How
Hmm.
can digital twins help optimize biomass supply chains for renewable energy production?
Okay, suppose you set up a one biomass plants in city. So in that area, you don't have lot of supply of biomass. So you need to take supply from another cities or another village or another states. Okay, so from that situation, you need to track all those things, that biomass supply chains through digital twins. So every that supply chains you have to tracking through sensor, and you have to control. So each supply chains you can optimize in the biomass supply chains.
Thank you, sir. There's a last question from Suganya C. Now, as we are moving towards electric
Hmm.
vehicle, hydrogen fuel, does research in bioenergy production from biomass have demand?
Ah, yes, it's a great question. See, the electric vehicle hydrogen fuel is okay. Hydrogen fuels also is a side by side, and electric vehicles also side by side. But it is not a look like that. It is a your permanent solution. After some days or some years, that electric vehicles, that battery will be waste. That waste material, what to do? So everything will be side by side, will be continuous going on, because if we remove the fossil fuels, so continuously we don't think about that electric vehicle or hydrogen fuel will be cover all those things, because still it is research is going on. The efficiency of production of hydrogen fuel is not too much. Okay, so that's why. And biomass, bioenergy also it is emerging production. Even you see that hydrogen, you can see the hydrogen fuel also produces using biomass, some bioenergy production plant. This is also one more thing. So bioenergy is the is possibility to next generation or next year, next 50 years. You can see the bioenergy will be the most attractive energy production system.
Thank you, sir. We thank you once again for sharing your time, expertise, and vision with us. Let's all take this opportunity to reflect as of now we can apply these insights within our own discipline and work together towards a more sustainable, data-driven energy future. Thank you for that, sir.
Thank you. Thank you. Thank you.
Thank you, sir.
Thank you.
So we now move on to the fourth session. I request all the participants to stay tuned till the next speaker joins us. Dr. Prashant Majumdar, sir.
Yes, sir.
Is the voice audible, sir?
Yes, it's audible.
Okay. So we'll start at 7:30 sharp.
Okay, sir.
So, very good afternoon, everyone. For our current session, we have Dr. Prashanto Majumdar, Research Associate, Interdisciplinary Center for Energy Research, IISc Bangalore, who will discuss emerging solar energy technologies, trends, prospects, and sustainability. So, let me introduce about our today's speaker. Dr. Majumdar is currently working as DST ACRB sponsored research associate at IISc Bangalore. He completed his PhD in solar energy from NIT Mizoram, MTech from NIT Agartala, and BE from Tripura Institute of Technology. His research area include alternative energy sources, energy storage, sustainable energy usage, waste to energy, and drying technologies. He has published 4 patents, 16 SCI and Scopus indexed journal articles, and book chapters. He previously served as assistant professor at Savitha University, Chennai, and as project scientist at Tripura State Council for Science and Technology, Government of Tripura, where he has executed DST-sponsored projects. So thank you so much, sir, for being with us today. Now the stage is yours. You can continue, sir. Thank you.
Thank you, sir, for your nice introduction.
Thank
Good evening to everyone. So today's my topic is emerging solar energy technologies, trends, prospect, and sustainability. So these are the highlights of my presentation. First, introduction, then sustainable development goal of the United Nations, then environmental sustainability, then energy storage and waste energy recovery overview, then case study on the design of a sustainable solar energy system. So first of all, what is sustainability? Sustainability means the meeting of the present needs without compromising of the future generation well-being and to encompass the environmental, social, and economic factors to achieve the balanced long-term viability. The three key pillars of the sustainability are: one is environmental protection and enhancement, then economic development, then social progress. Environmental protection and enhancement means we have to develop any system or any process or any product, whatever, so in which the resources to be used, that is the renewable energy resources or any bioproduct or anything, so that it will less hamper the environment. And also the emission from that system or the manufacturing of that process or any system or any machines or that is the end product of that the end product will not hamper the environment significantly. And the economic development means the we have to look for the alternative sources, like as a conventional way, we use the fossil fuel, petroleum, coal for the power generation or any other purposes. And for the as we know that India does not have any oil resources, we have to import the oil, so that the huge amount of that is the money we have to spend for importing of this oil. And if we can develop or if we can produce any alternative fuel, like nowadays various research is going on for producing the biofuel and like that, so that the economy of this so that is the expenditure on importing the fuel will be reduced and the economy of the country will be developed. And the social progress means that is the we have to develop a system or we have to produce any material or anything, so that it can be used, it can be accessible to the everyone, and cost of the product also will be accessible to everyone. Like for the fossil fuel prices rising day by day, so it is hampering the mainly the middle class people and the lower class people, lower middle class people, and also the lower class people. So if we can generate the alternative energy sources which the cost is minimal, so that it will be accessible to the that means the lower income people and also the middle class people also. So and also this is the social impact of the sustainability. Then the United Nations also adopted total 17 goals, that is sustainable development goals. It is ambition 2030. That is target is 2030. Within 2030, that is the United Nations that is set a target to accomplish all these parameters in various disciplines, various sectors, and various service or any manufacturing sector or any sector. So there are total 17 goals are there. So as the theme of this faculty development program is that it is energy and climate based, and my topic is the solar energy based. So that is will come under the goal 7, SDG 7, that is the affordable and clean energy, accessible of affordable clean energy to everyone. That is goal 7. And climate, which is also climate action, which will come under the goal number 13, SDG goal 13. So our focus for this particular session is the SDG 7, that is the access of affordable clean energy and the cheap energy for everyone. And what is Sustainable Development Goal 7? That means ensure access to affordable, reliable, sustainable and modern energy for all. So that means, suppose for example, solar. So it can be easily accessible in most of the places, for most of the places around the world, except some location. And also it is affordable. It is almost zero cost, except the investment cost for fabricating the system, and the operating cost and the running cost is very less. The running cost is means zero, almost zero. Only the operational and maintenance cost is there. And reliable and sustainable. Reliable, this is the most important thing, because the concept of solar energy is not new. It introduced is many years ago, and also everyone tell the solar energy, solar photovoltaic system, solar thermal system, and use the alternative energy sources like use biofuel instead of fossil petroleum, and use wind energy, use energy. What's the main challenge of implementing of this renewable energy sources or renewable energy technologies is the lack of reliability. Because unlike the fossil fuel, it's the availability of this energy sources are not continuous, and also storage capability of this energy sources is also limited. There are many limitations are there. Though various research is going on to enhance to develop the storage technologies, so that we can store these energy sources for a long time when this is not available. Our solar energy is only in daytime it is available. In nighttime it is not available. But in the industry, this operate 24/7. And when we healthcare facilities or any other service sectors also is operate 24/7 hours. So for these sectors, that is the 24/7 hours energy supply is required. So for these cases, we need to store the energy, and so that we can use while the energy sources is not available. And also in the rainy season also solar is not available, so that, but we cannot wait for this when the rain will gone and the solar will arise. So this is not that's why this is not reliable, still not reliable in many sectors. So we have to look into that. That is the main important thing. And the universal access, that means provide everyone with access to affordable, reliable, and modern energy, and increase the share of renewable energy sources in the global energy mix. So anything that we cannot eradicate anything in a day, and we can introduce the new technologies. So gradually we have to substitute of the old technologies, or the old energy, or the conventional energy resources, and we can increase day by day, increase the share of the renewable energy sources day by day in the global energy mix. And energy efficiency is another important factor, because in the at present, that is the efficiency of the energy efficiency of the solar system is not that much. Still it's below 50%. So the research have to be conducted. Also, still many people are doing research, and also the stockholders are concerned about this, how to improve this energy efficiency of the solar system and other renewable energy sources. And infrastructure and technology. So that means if we suppose in the fossil fuel system, like the coal-based thermal power plant or any fuel-based, gas-based thermal power plant, that is the energy, the electricity is producing continuously, and also the grid transmission system is there with this power station. But in the solar system, in the solar thermal system or solar photovoltaic-based electricity generation system, mostly are independent systems, standalone or independent. And also the wind generation, wind power generation system also is mostly standalone system nowadays. So we have to look how to make it possible to connect it with the grid power system, so that when the energy sources, solar energy or wind energy is available more than need, so that we can supply this through the central grid system, so that the production of the solar energy system or wind energy system or whatever renewable energy system will be beneficial, and there will be less loss. Because otherwise, in that, suppose we have made any solar system or any solar power generation system, and in the daytime the solar energy is sufficient and we produce the huge amount of electricity, but our need is less, so the remaining will be lost if it is not connected to the grid electricity system. So that thing has to be considered. Still in this aspect, still is looking the system. The international cooperation has enhanced the cooperation to facilitate the access to clean energy research, technology, and the investment. Also, investment is required, and various government also is trying to invest. That is, giving the subsidy so that the people will be encouraged in implementing the system. Like government of India recently introduced the Pradhan Mantri Muft Bijli Yojana. That means that for every household or supply, every household they can generate their own electricity by installing the solar photovoltaic system at the rooftop. And government is giving the almost 50% subsidy for this system. So these are the steps from the government also has to be taken timely, time to time. And environmental sustainability is the most important criteria, most important pillar of the sustainability criteria. And there are 4 aspects in environmental sustainability. That is, first one is sustainable design, then sustainable operation, then sustainable maintenance, then life cycle analysis. Sustainable design means, first of all, for introducing any system or for fabricating any machine or any system or any designing any process or any product. First of all, we have to design, we have to plan, we have to make prototype, and we have to either physical or any simulation prototype. And accordingly, we have to do analysis after making the prototype or any simulation design. We have to do simulation if any things has to be done. That means modification is required. We have to do that. So this will come under the sustainable design, and it will abide by the energy and environmental management policy of International Standard Organization 2001 and International Standard Organization 14,000. And it broadly include the energy source selection, then recycling, system and resource selection, product and byproduct identification and execution of re-engineering, lean engineering, and system engineering. That means energy source selection. First of all, for designing any system, first of all, we have to select the energy sources. We have to focus, primary focus would be the selection of the alternative energy sources and recycling system. That means we have to reduce the waste energy. We have to minimize the waste, and so that for this circular economy have to be introduced, so that the minimization of the waste would be done, and also the system efficiency also will be, and the energy utilization ratio would increase. And the product and byproduct identification and the reuse of the byproduct also have to be identified. And then execution of re-engineering. Re-engineering means that as a first making a prototype, and then evaluation of the performance, then redevelopment. That is the re-engineering. And lean engineering, that means the minimize the waste, so that the increasing the productivity and also the energy utilization ratio. In the renewable energy system, it is said that the energy utilization ratio is more important than the energy efficiency, because how much energy we can utilize by circular economy or waste energy circular utilization or waste recovery system, that is more important. And system engineering means that is the incorporation of the multiple aspects, that is the combining of the multidisciplinary systems for improving the total complete energy system or complete any production system. That is will come under the system engineering. Then energy transition and sustainability. India's energy mix is set to undergo a transition from fossil fuel to renewable energy 50% cumulative installed capacity by 2030. That means Government of India's vision is that, in compliance with the Sustainable Development Goal of the UN. And Government of India also had launched National Solar Mission and National Mission for Enhanced Energy Efficiency to achieve the non-fossil fuel based capacity, promoting energy efficiency, and has pledged to reduce the emission intensity of this GDP by 45% by 2030. So this is the Government of India initiative. And as I told also earlier that there is a reliability of the renewable energy system is a main concern. Unlike the conventional energy sources like coal and nuclear, renewable energy cannot be stockpiled, and generation from these sources cannot be controlled. Like coal, we can store it for a long term. But the solar energy, we cannot store it. But in every day, the sun rises, and in every day we can get it. We cannot stock it because there is a limitation of the storage of thermal energy system also, because at present the most common thermal energy storage system like sensible storage like rock or anything, and also the PCM based energy storage system like latent storage like wax or any other like this, and bricks, and these things cannot store the heat energy for the long time. Suppose in the daytime, when the solar is available, in the heat exchanger, we can store the thermal energy into the either wax or any rock or any sand like this or water, and with and that thermal energy we can use it at the night time only. But we cannot store it for the 3-4 days or 1 week. Can store it. The limitation is there. Like coal, we can store the coal for the long time. And also the generation from these sources cannot be controlled. We cannot control the generation because sun power, sun radiation we cannot control. It is out of our hand. But though currently there is some research going on the thermochemical energy storage system, metal hydride based thermochemical energy storage system, which is combined of the thermal energy storage and hydrogen energy storage. That is another recent trend of use of hydrogen fuel. And there is another challenge in storage of hydrogen. There is another challenge. So the combining of this hydrogen storage and the thermal energy storage under that is by using the thermochemical process metal hydride system. That is another approach, and though it is not developed that much, but research is going on that system. So we have to look into that so that we can increase the storage duration of the renewable energy sources. And the challenges with renewable energy sources arise due to their varying nature, time, climate, season, or geographical location. It also that it is out of our hand, and also it is based on the natural that is the location, geographical location, also climate based, and also timing based. In daytime it is available, nighttime not available, and during rainy season also we are not it is unpredictable. So these parameters we have to consider while designing any renewable energy based system, so that the system will be reliable. Otherwise, that's why otherwise if it is not reliable, the people will not be encouraged to use this. Though government of India is implemented various schemes like rooftop solar power generation system, and the government also giving the subsidy, but still the people are not that much interested for getting that scheme, because people are in fear that about the reliability of the solar system, because after investment of so much money, so the people are in fear whether it will be reliable, after how many years we can use it. So that fear is there. So that means the confidence should build among the public, so that the public will be encouraged to use this renewable energy system. The need for energy storage system. So the intermittent nature of renewable energy sources, like notably mainly solar, wind, or run-of-the-river hydropower project. In the last hydropower project, the water reservoir is there, so that we can control the water reservoir. That is the flow of water. We can close and open the gate, reservoir gate. But in the run of the river, like Pico hydropower project, the water turbine is generally fitted on the across the water flowing in the river, so that we cannot close and open as per our choice. So in that case, the energy storage is required. The incorporation of the significant amount of variable intermittent energy into the energy mix presents a challenge for maintaining the grid stability and uninterrupted power supply. And the current renewable energy technologies cannot balance the power market demand through immense and inventory storage, because as I already discussed these things, because the various health sector and food and agriculture and the service sector 24/7 power supply is required, and also the grid stability for continuous grids, uninterrupted grid stability and uninterrupted power supply, continuous supply is required. So in that case, to maintain that, the energy storage system is required. And also the gap between the energy demand during the peak time and supply can be caused by the difference in energy availability time and consumption. And during the peak time also cost goes rise. So we have to consider all these things, and also the energy storage system should be developed so that the renewable energy system would be, it can make reliable. Storage of energy will help in bringing down the variability of generation in renewable energy sources and improving the grid stability, and also having the energy power shifting and support the service and last renewable energy integration. And it will also benefit the consumer by bringing down the peak deficit and peak tariff and reduction of carbon emission, deferral of transmission, distribution loss, and energy arbitrage. Then waste energy recovery. It is another aspect, because in many thermal systems, the heat loss is the very challenging aspect. From the if any fluid system, from the exhaust fluid, any flue gas coming out from the exit of the system, or any fluid like water or fluid coming out from the system is having the higher thermal energy. So that and also the heat loss from by conduction and convection through the system boundary, also to the outer towards the surrounding, that is a serious concern. So we have to restrict this heat loss, and that can be possible by circular economy and also the recirculation of the system. And waste heat utilization can improve the gross efficiency as much as 20%, because due to this waste heat, the thermal efficiency of the system is less. So if we can restrict this heat loss, we can improve the efficiency of the system as much as 20%. And while designing any heat recovery system, one should consider the quantity and quality, and the operating schedule, composition, phase, accessibility, and transportability of waste stream, metallurgical properties of the heat exchanger material. That means how much for selecting of the material or selecting of the waste heat recovery system or waste heat material, whether it will be sensible heat storage material or latent heat storage material or thermochemical storage material. First of all, we have to know the how much exhaust heat is available and average. And based on, because the melting point temperature of the all the material is not same, because it depends on the material properties. So that's why the quantity and quality of the waste heat has to be identified. That operating schedule and composition for the how much time it will be available and how much interval it is available, and the phase, whether there will be the phase change material or sensible heat storage material or thermochemical storage material like heat and hydrogen storage like this can be implemented. And transportability of waste stream, that is also if the transportation distance is higher, there is the huge chance of transportation loss is there, like in the electricity transportation system or in a thermal energy transportation system. If this is very higher, so there is a chance of heat loss, transportation loss of heat or electricity, whatever. So you have to consider all these things and have to implement the proper insulation into the system. And metallurgical properties of the heat exchanger material, that is all are interconnected with the system. And based on the temperature, there are the waste heat are differentiated into three categories. One is low grade, that means less than 100 degrees C, medium grade 100 to 400, and the high grade greater than 400 degrees C. So then generally in the solar energy system, it will come under the low grade energy, that means less than 100 degrees centigrade. Because in the solar system, that is in the most of the cases, it will not go up more than 100. And the storage of high grade energy is easier compared to the low grade energy. That thing, so the research also going on, so how to store the lowest low grade thermal energy system, and research also going on. So this is the solar energy, combined solar energy system with the room air conditioning system. So here in the solar collector is there, that is the solar thermal collector. And at the solar thermal collector, so there is at the upper portion there is the solar absorber, and the below the solar absorber there is one channel is there. and through this channel, the fluid is passing, either air or water. And this water, suppose here in this picture, this air is passing through this system, and that this suction fan is there. This suction fan will suck the air, cold air, and that cold air will pass to the solar air collector. It will get heat. It will collect the heat from the solar absorber, and that hot air will passes to the packed bed storage tank. That is the heat energy storage material. It is either sensible heat storage or latent heat storage material, and that hot air will passes through the building or the building air conditioning system. So like this system, by using like this system, we can utilize the excess heat from the solar air collector or the building air conditioning system. And in the daytime, when the heat is in the daytime, suppose if this hot air is being utilized for any processing system, and in the night time, if the heat is being stored in the packed bed storage system, and that heat can be utilized in the nighttime air conditioning for the room heating system. So that is it is a combined system, so that the waste can be minimized and maximum utilization of solar heat energy can be done. And it is PVT PCM system for household hot water supply. These are similar things. Here the photovoltaic thermal system and the PCM, that is phase change materials. Here in earlier system there was sensible heat storage material was there. Here in this chamber, like stone or sand or like this material was there, but here the phase change material was used. Here at the upper portion of this solar panel, or in the photovoltaic cells are there, and at below the photovoltaic cell there are PCM material are there. And that PCM material getting heat from the photovoltaic cell, and it get melted and stored the heat energy. And there are some pipe are there, the copper tube pipe are there, and through this copper tube pipe we passes the fluid, either water or any other fluid passes the, and that fluid will get the heat from the PCM material, and that hot fluid we can pass to the water, that hot water or any fluid, that here the hot water is used, and that hot water can be is passed to the household utilization. So that means in this combined system, in one way we are getting the electricity from the photovoltaic system, and also we are getting the hot water supply for household purpose. Otherwise, if the combined system, the hot water supply system is not there, the solar panel will get heated, and if the solar cell is get heated more, is the electricity generation efficiency is also reduced. So it is much needed to consider the thing how to keep cool the solar cell to increase the productivity of the electricity generation of this from the solar cell. Now, case study on the designing of a sustainable solar energy system. In the solar energy system, there are two aspects. One is the solar thermal, and that is solar photovoltaic. So here in the case study, so I'll show how the solar energy system can be designed for the sustainable use. Because there is a concern about this, I already told that in the solar energy system, that one main issue is the sustainability, the reliability of the system due to uncertain solar energy sources. So here is the solar thermal system and solar dryer. It is scalable and is adaptable. So here one solar thermal system is there, and here this both are the solar thermal system, and here the solar photovoltaic system, and this is the drying system. So drying is a process is being used in the various industrial purpose, like food industry or pharmaceutical industry or apparel industry or many other industry, paper and pulp industry. This drying process is used. And in this drying process, we require the hot air to be supplied. And for this supplying this hot air, we can use that is solar thermal system. Here the various components are like solar air heater, and this data acquisition system is required for this measuring the various parameters of the solar parameter or any process parameters. And then solar photovoltaic system is there for operating the system, operating the suction pump to make the system solar reliant, and battery and charge controller for for controlling the photovoltaic system, and control panel. And this in the right portion, that is the drying system is there, the blower, electric heater, and hot air emitter for measuring the hot air emitter will be used for measuring the airflow. It is another important parameter. Recirculation duct, that is the circulation strategy. It is for utilizing the waste heat, and that waste heat can be utilized for the further process. Now, design consideration for solar dryer. So, how to design? This is the important thing. How to design a system sustainability. So, first of all, the thermal load calculation. In any thermal system, first of all, we have to estimate the thermal load. How much thermal energy would be required for the proposed system. In this system, in the drying system, that means the quantity of moisture to be removed. That is, for any product, how much moisture to be removed from the product. So that is required. That is to be estimated. Estimation of that to be required for measuring that. That is for calculating the thermal load of that system. Then heat energy estimation to extract desired moisture quantity. Then air velocity estimation. So how much air flux is required for my process. Estimation of the mass flow rate from the energy balance equation. Then superficial speed calculation of the hydrodynamics analysis. Then sizing of the solar air collector. Because sizing, we have to, as per our requirement, how much thermal energy is required and how much air velocity, air flux is required. So based on that, we have to design and fabricate the size, so at a particular size of solar air collector. Otherwise, if it is smaller or larger, if it is smaller, it will not be, it can meet our demand. Or if it is larger, there will be heat loss. So that the perfect sizing is required. It will be dependent upon the identification of the flow process, either laminar flow or turbulent flow process. Then convective heat transfer coefficient determination using the Nusselt number. Then surface area estimation for the solar air collector using convective heat transfer equation. That is absorber, solar absorber area estimation. Because the convective heat transfer depends upon the surface area. Then estimation of the photovoltaic system, which will depend on the electrical power load calculation, and estimation of battery from charge capacity and the usable capacity of the battery, and estimation of photovoltaic from the electricity demand and available sunshine hours. And the development of this drying system was designed basically for the locally harvested agro-horticultural produce, considering their huge global market potential. This system, drying system, was basically developed for drying of the agro-horticultural produce of the locality, because it has huge global market potential. And also in the village area, people generally dry the product on the open sun, by spreading the material on the road or any open ground. But due to uncertain weather and uncertain solar energy, and also intermixing of various debris and insects, so there is a very unhealthy process. And also it takes the prolonged duration to dry the product. So for the sustainable drying operation, and to make the drying machine, this is the drying system, sustainable, so have to design this sustainable drying system. In conventional way, there are electrical energy-based dryer are available in the market, but the electrical power consumption, and nowadays the electricity tariff is very high, so it cannot be affordable for the poor farmer to use the electricity-based dryer for drying their product, and to make them to the market and to make them available in the market. So for that, in order to eradicate these difficulties, we have to design a solar-based dryer in a sustainable way so that the people can rely on that drying system at minimal cost. Then the moisture content of the maximum fresh agro products varies between 70 to 90%. First of all, we have to estimate. First, we have to select the which product we are going to dry, either agricultural product or any cloth or any paper or whatever. How much moisture is existing in the fresh product. In the agricultural product, it is 70 to 90%. And desired final moisture content at which the shelf stability can be retained is 5 to 12%. That means after the final product, the moisture quantity should be 5 to 12%. We should not dry it up to the bone dry process. That is 0% moisture content is not desirable. So that thing also we have to identify. The minimum temperature required for the drying process from the various literature or any simulation study, we have to identify the minimum average temperature required for optimum drying operation. That is identified as 50 degrees C. And mass flow rate, we have to estimate how much mass flux is required to supply for particular drying operation. Then quantity of moisture to be removed by drying process by this formula, that is MV. That is Mi into MCI minus MCI by 100. That means Mi means the initial mass of the raw fresh product to be dried. Is the how much, that is the inventory size. And moisture content I, MCI and MCF. That is moisture content of the initial moisture content, that is moisture content of the fresh product and moisture content of the final product. So by this equation, from this equation number 1, you can find out the how much quantity of moisture to be removed in this proposed drying process. Then in the equation number 2, you can calculate how can how much moisture content is present in the product, where MW and MD are the mass of water and the mass of dry matter in the product. Then amount of heat energy to be supplied during drying process to evaporate the required amount of moisture from the product. So in the equation 1, we calculated the amount of moisture to be removed. Now, how much heat energy is to be supplied to remove that quantity of moisture from the product? That is QE from the equation number 3, right? MV LFG. That is MV means the mass of the product, that is quantity of moisture to be removed from the product, and LFG is the latent heat of evaporation of the moisture. Because moisture, that is the water content present inside the product, it will remove by that means in terms of vapor. Suppose the water content present in the crystal structure of the product, it will come out from the inner core to the outer surface. Then from the outer surface of the product, that moisture will evaporate to the surrounding. So that's why the latent heat of evaporation of moisture is required to be considered. Then the latent heat of evaporation we can calculate by using the equation 4, which is depends upon the universal gas constant and the surface temperature of the product and the surface temperature of the surface temperature of the product and the air temperature and all these things. Tx is the average surface temperature of the product. That means the product outer surface temperature we have to estimate from the weighted mean of dryer inlet temperature and ambient temperature. So dryer inlet temperature is we already know how much temperature is required for this particular process. Suppose 50 degrees C is required. Minimum temperature is required 50 degrees C. Ambient temperature we can measure from the instrument, and this from this ambient temperature and the dryer inlet temperature. That means drying air temperature. We can estimate the product surface temperature from the equation number 5. And the required supply rate, air supply rate in the solar air collector can be estimated from the equation number 6. That means mass flow rate of air, then CPR, the specific heat, then TA out minus TA in. That means the temperature out from the dryer and temperature in. TA in means temperature in of the dryer. And these are the assumed and estimated parameters for calculation of this process. Maximum moisture content is assumed as 90%, and desired final moisture content is 9%. That is the fresh product. We are assuming that the moisture content is 90%, and the final product is 9%, and the inventory size is 2 kg. Then moisture extraction quantity is from the equation number 1. We can calculate it at 1.78 kg. Ambient temperature in the locality where the dryer is placed, it is measured as 25 degrees C, and ambient relative humidity is 85%, because relative humidity is another important parameter in drying process, because the air has to remove the moisture from the product, so that the air moisture content, air relative humidity is another important factor. If the air relative humidity is higher, so that it cannot extract the moisture from the product. So that our intention should be to reduce the air relative humidity as much as possible by some other means, like dehumidification process. And mean product surface temperature, it is calculated by the equation, and latent heat of evaporation of water, it is established, and heat energy to be supplied for drying, it was calculated, and estimated drying time, it was for the pre-experimental process, it could be estimated. Then hydrodynamic of fluidization system, because as it is fluid is passing, it is air is passing, so that is that is the fluid, so that we have to consider the hydrodynamic phenomena, and the required velocity of air in the fluidized bed column was estimated on the basis of minimum fluidization velocity. That means how much the velocity of the air should be at which the product would behave like a fluid. It is product fluidization would introduce, and that minimum fluidization velocity can be determined by the Curie-Levis-Field correlation by using the equation number 7, and that is depends upon the various parameters of the product and also the drying air, where epsilon mf is the void fraction or bed voidage. That means the bed voidage between the product and the air in the drying chamber, and mu mf, psi s, and the dpm are the sphericity and the mean particle size, the particle size of the product, and the mu are the density and viscosity of the fluidizing air. That is rho g and the mu. G is the acceleration due to gravity, etc. Then void fraction can be calculated by using the equation 9. That is the void fraction equal to 1 minus volume of the product divided by volume of the bed. Void fraction in the some particular bed or some particular duct in a chamber, how much void is present in between the product. So that we have to estimate. So that we can estimate by using the equation number 9. It is m and rho are the mass and density of the product and the bed. However, the void may be treated as empty space. Is told. The density of the bed can be calculated by using the mass mp by vb. That is, vb is the volume of the bed. We can calculate this by using the dimension from the bed. We can calculate the volume. Also, dfc and sb are the diameter of fluidization column. Diameter and the height. From the diameter and height, that means from the outer dimension, or the dimension of the column, we can calculate the volume of the bed. Then for the non-sphericity, sphericity means for the non-spherical samples may have their shape quantified by the term sphericity. That means the surface area of a sphere of the same volume divided by the actual surface area of the product sample. So the mean particle size of the non-spherical particle can be calculated by using the equation 13. That means in reality, all the particle or all the product are not in spherical form. So for that product, we have to calculate the sphericity of that non-spherical particle by using the equation 13. And the minimum fluidization velocity was estimated to be 0.02 meter per second. That means at this particular velocity, that means this is the minimum flow rate of air we should maintain so that the product will fluidize and drying can be started. But at this also, this is the minimum velocity. But for the effective drying operation, superficial flow rate is required. So that is calculated as 1.13 meter per second. So these are the assumed and estimated parameters, like density of the samples. We have to calculate this dimension, so we can measure by areas. Then the acceleration, gravity, density of the air at 50 degrees C. That is the standard. It is available. Standard data is available at 50 degrees centigrade on a particular drying temperature. What would be the density of the air, viscosity, and conductivity, thermal conductivity of air at a particular temperature? The diameter is the dimension of the column, and height of the packed bed and volume flow rate. Now, sizing of the solar character. we have to that is the sizing of the solar air collector so that it can produce the required heating effect. First of all, the hydraulic diameter we have to estimate from the equation 14. The required air velocity in solar air collector can be estimated after the superficial velocity of iteration. We have to multiply the factor of safety is required because there will be some losses, heat loss by conduction and convection from the side wall, so that we cannot control. And then Reynolds number was calculated to check the nature of airflow in the solar air collector, because in any fluid system, because in a thermal fluid system, the Reynolds number flow, laminar or turbulent flow, we have to consider whether the airflow is laminar or turbulent. So by estimating the Reynolds number, we can find out whether it is laminar or turbulent flow. It was found that it is laminar nature of the airflow was there. And also we have to determine whether the heat transfer is the natural convection or post-convection system. Also you have to determine by using the equation from the Grashof number and Reynolds number correlation. If it is less than 0.1, it is a post-convection, and it is greater than 10, it will be a natural convection. Then the Grashof number is calculated using the equation number 16, where beta is the coefficient of thermal expansion and the average surface temperature of the solar absorber correspond to the solar radiation. That we have to estimate, and the climatical scenario of the experimental location are approximated to be 60 degrees C. That means considering the surrounding location, that's the locality where the dryer is placed, considering the ambient temperature, based on the ambient temperature, the surface temperature of the solar absorber was estimated as 60 degrees C. Because the surrounding temperature, the ambient temperature was estimated as was found at 25 degrees C in that locality, and compare this on the basis of that, the surface temperature of the solar absorber was estimated as 60 degrees C, and convective heat transfer coefficient was quantified using the Nusselt number by using equation 17. It is convective heat transfer coefficient equal to Nusselt number into delta by ds. That is delta is the thermal conductivity, and the hydraulic diameter, ds is hydraulic diameter. LT, then where LT can be estimated, Nusselt number can be estimated from the equation number 18, where LT can be estimated as from the equation here, that is the characteristic length can be estimated from this equation. Then the required area of the solar air collector can be estimated is equation from equation 19. That is convective heat transfer coefficient into area of the solar absorber into T of absorber, that is the temperature of the surface temperature of the solar absorber minus TA, that is the temperature of air. The required length of the absorber was found to be 3.12 meter. That is like this, by using all these equations and all these estimations, we can decide the optimum dimension of the solar air collector, so that we can generate and we can supply the required heat energy for the proposed process heating system. Then estimation for battery and photovoltaic module, and we have to estimate the how much capacity of battery and photovoltaic system is required for operating the suction fan and blower. Also, the total power consumption by the pump per day is found to be, it is the total power rating into running time. How much time per day it will be run, on that it is depend upon. And power rating is the standard of that particular pump. Energy input to the converter system can be estimated by the following, that is the equation number 21, that is the conversion of energy have to be estimated, and usable capacity of the battery after among the total capacity, how much it can be usable from the rated capacity into depth of the discharge. It can estimate from the equation number 22. And the required charge capacity of the battery, it depends upon the voltage of the pump, that is suction pump, and the converter. And the desired number of batteries can be estimated from this equation number 24. Then energy input into the battery can be computed from the equation number 25, that is the E of battery from the E of converter by efficiency of the battery and the conversion efficiency. The energy input to the charge controller, this can be generated on the photovoltaic panel. This can be determined from the equation 26, on the which depends upon the charge controller efficiency. and the energy input to the battery. The total charge capacity of the photovoltaic panel also found out by this equation 27, and the total electricity need to be generated by the design photovoltaic module is estimated as from the equation number 28. And for generating this total electricity, how many photovoltaic module is of that particular charge capacity or efficiency can be estimated by using equation number 29. So for that, for the proposed system, and and also the based on the proposed electricity requirement, the number of photovoltaic module of the particular particular rating, photovoltaic rating and efficiency, the number of photovoltaic panel was estimated by this equation number 29. It was as 1.6, and is that is proportional to 2. That is 2 photovoltaic panels required, and it was assumed that the system will run for 6 hours per day. Then these are the estimation for battery, and this is a photovoltaic motor. This is the voltage and power rating. These are some standard rating of that particular instruments is available in the market, and the battery power efficiency of the battery, and photovoltaic system voltage, converter efficiency, and the energy input to the converter, acoustic charge capacity, energy input. So all these things, all these parameters we have to consider while designing, before designing of any solar photovoltaic system. For any, suppose we are not only this drying system, suppose we are planning to install photovoltaic system for power generation in our rooftop. So for that also we have to calculate this these things, means how much photovoltaic panel a particular specification is required. So otherwise, if we, without any calculation, if we simply just purchase and install it, so it will not meet our expectation and our demand, and also we cannot rely on that, so that the system will fail. So that's why the proper calculation and proper design is required before implementation of any system, especially in this renewable energy system, because it's very sensitive, and also the energy system is very lower, because the lower thermal energy is only the less heat energy is available, and also the temperature is less. So for this, the precise control and precise calculation is required. Here the system for designing a fabrication of solar air collector for sustainable drying industry. So in many solar system, there are many example is there that it is not reliable, because the heat energy generating is not sufficient, and it cannot meet our demand. So that we have to design and fabricate the solar thermal system in such a way that it could meet our demand and throughout the year. So aiming of that, so this solar thermal system was designed and fabricated so that it could meet the heat energy demand for the particular process or as per the requirement. So here in the conventional system, in the solar air collector or solar air heater, there's a flat plate absorber is used, like flat metallic sheet, flat aluminum sheet, and also with black painted absorber is used. But here, the semi-hexagonal shape absorber was used. To increase this semi-hexagonal shape, increase the surface area, the solar absorber surface area, because the heat transfer depends upon the surface area. So by this incorporation of this semi-hexagonal shape, the surface area of the absorber is increased. And also the helical spring was incorporated at the semi-hexagonal groove at the top of the absorber. This function of this helical spring is to introduce that air turbulence. This air turbulence will increase the convective heat transfer coefficient, so that the maximum heat energy can transfer from the absorber to the air, that is process air. And also there are underneath the hexagonal, that is the hexagonal channel is used, that is honeycomb channel. Here that is double pass air heater was used. That means the first initially the cold air will pass through the underneath channel, and then it will get some heat or preheated by getting the heat from the below portion of the solar absorber. After that, after preheating, that air, that partially heated air will flow through the upper portion of the absorber, and so that it will get the maximum heating from the top portion of the absorber, which is exposed to the open sun. And this novelty of the pattern is that in a conventional solar collector, the flat plate absorber is typically employed. But yes, semi-hexagonal cross-section solar absorber was used to maximize the surface area and heat transmission efficiency. And to increase the air turbulence and heat transfer, helical spring was mounted. Because in turbulence flow, that is the heat transfer efficiency is increased. And for optimum utilization of the absorbed heat energy, provision of double pass was used, because from the underneath of the panel, that is the lower side of the solar absorber, some heat energy is getting wasted if you not utilized it. So that's why double pass was used. So initially the air is being passed from the underneath portion of the absorber so that it gets preheated, and after that preheated air will passes through the upper portion of the absorber. Like in the biomass system also, before getting it into the biomass combustion or biomass gasification, it is need to be preheated so that the system efficiency will be increased. And to limit the heat loss by the radiation from the top of the absorber, double glazing was mounted at a measured distance. Here the double glazing was used because there is a concept of irradiation that it cannot radiate in the vacuum. That means vacuum channel is maintained between the two glazing. It is the upper and the two glazing are there at a certain distance, like 5 centimeter distance apart, and that channel, that chamber, the particular channel is kept at the vacuum so that the heat energy cannot passes through this vacuum channel between two glazing, so that the radiation heat loss from the upper absorber is restricted, and the maximum utilization of heat energy, heat transmission can be possible from the solar absorber to the flowing air. Now we have to performance evaluation of this of the solar thermal system. So I have to like re-engineering. That the concept of re-engineering have to apply. That means after the fabrication of this system, we have to perform the we have to evaluate the performance, and if any modification is required, so that we can should be done in the further fabrication or further research. So first of all, the incident solar energy input in the solar air collector is estimated by using the equation 30. That is, the usable heat energy gained in the solar air meter by means of air heating is can be estimated by equation number 31. That means where I is the solar intensity. This we can find out by the by using the pyranometer. You can estimate, and also various sites at the like Solcast, also various sites at the solar data. It can be readily available in various in every location worldwide. Then area of the solar collector have to be is already calculated, already estimated in the earlier section. Then alpha and tau. Alpha is the absorptivity and the transmissivity of the glazing. It is the top glazing, because the absorptivity should be high so that the solar energy can be absorbed in the solar absorber. Transmissivity, and then T out is the outlet temperature from the solar air collector. That is the how much temperature of the outlet air, and that T ambient, that is surrounding temperature. The solar fraction is the proportional total energy required in any solar system. This two important factors. One is solar fraction and solar heat fraction is very much important to be calculated, because what is solar fraction? That is the proportion of total energy required for the process that comes from the sun. Suppose for any system, suppose for this system, here the some heat energy is required and electrical energy also required. So out of this total energy, how much energy we are getting from the sun? So that is the solar fraction. And then solar heat fraction. Solar heat fraction means out of total thermal energy being utilized in the particular system or in a system, how much we are getting from the solar. That is solar heat fraction. So our target should be should increase the solar fraction and solar heat fraction, so that the system would be completely 100% reliable, rely on the solar energy. So the solar heat fraction and solar fraction should be high as much as possible. The performance of this system is that the designed SSC could be scaled up in a location for drying process based on the, because this system is designed in such a by keeping the provision of scale up scope. So it can be scaled up in any location and for any inventory size or for any process and any location having the different climatic condition. And for designing, as I already mentioned, that various assumed and estimated parameters in the tabular format, what are the parameters is required for determining the sizing of the system, so that it can scale up based on our requirement and based on the capacity of the plant and based on the local climatic condition and also based on the product physical properties, physical and thermal properties also of any particular product which are going to dry or any other process heating application also. These are the important factors like intended class of product, climatic condition, desired drying temperature, what temperature is required, because for this desired drying temperature is not same for all the products. Like for cloth, for there is in various cloth, it is mentioned in the tagline tag that it should be washed in a cold water. The hot water cannot be used. So like that, so that this temperature have to be maintained for every product. So these things you have to take reference from any various literature or any established data, how much temperature any product can sustain. Then the current SSC output temperature was recorded to have increased by a maximum of 52 degrees C and average 40 degrees C. So that this is a very significant achievement, that there is from the inlet to outlet temperature difference is average 40 degrees C and the maximum 52 degrees C. So that means this is a significant improvement compared to the typically designed solar collector. So that means we can get 52 to 52.73 degrees C temperature rise. This much of temperature we can get above the ambient temperature. So that means if the ambient temperature is as assumed is 25 degrees C, so if it is average temperature gain is 40 degrees C, so that means it is 65 degrees C outlet temperature we can get. So 65 degrees C temperature is sufficient for any drying applications or any process heating application. Then developed SSC was capable of supplying at least 155.86 watt per hour heat energy, which is quite more compared to the projected energy level. So initially it was estimated that the heat energy required for the projected process was 125.82 watt per hour. And in this system, it was at least 155.86 watt per hour heat energy was produced. And so heat fraction was found was almost 1. That means all the heat energy required for this particular process we can get from this system. So no other means of energy sources is required for supplying the desired heat energy. And the highest recorded heat energy efficiency was recorded 40.5%. Energy efficiency was recorded 40%. And also the solar thermal conductor was reported to a sustainability index of 1.02. It was calculated. And the physical phenomena which is responsible for improvement of this particular novel developed solar thermal system is that the Reynolds number rises in the modified absorber collector and the boundary layer thickness of the plate surface diminishes. That is the boundary layer thickness, that is the mostly precision is reduced between the flat surface, absorber surface, and the air, and resulting in an increased quantity of heat transmitted from the absorber to the air. And the helical swing causes the air turbulence over the solar absorber and gains the more heat energy. Then dual mode produced bed drying system. So this is another invention, that is the solar energy based drying system. So here the modified produced bed drying system is advantageous with both the effect of direct solar heating and the cone angle. Here the design of the this drying chamber is modified and it is made its inclined position And the influence portion make of aluminum black painted from inside and insulated from outside will act as an absorber of solar energy. That means of this inclined system, inclined drying system, the half portion is the metallic sheet, which is black painted from inside, and which will get the solar radiation from inside, and which will act like a solar absorber. And the another half portion which is facing towards the sun, which is the polycarbonate sheet, which will like as a glazing of the solar air collector, so that the solar this portion, the metallic portion, will get the heating from the solar energy, and also this will be transmitted to this half portion, transparent portion, polycarbonate sheet. And if it passes in the from the side view, here the air suction fan is there, and the air will suck from the ambient, and it will passes through this chamber. And while the air is passes through this chamber, it will get heated by when it will be in contact with this heated absorber, and heated absorber will get heated from by taking the solar energy through this transparent polycarbonate sheet. And this conical shaped fluorescent chamber with a partial solar absorber wall will serve the simultaneous purpose of better fluid solid mixing and auxiliary air heating system. So the purpose of developing of this system is to enhance the efficiency of the system. That means the fluidization efficiency of the system. To enhance the fluidization quality, we modified this column, and also side by side auxiliary air heating also introduced by changing changing the shape of the chamber by introducing the two portion, or distinguishing the two portion. One is metallic absorber, another is the polycarbonate crystal, that is the transparent polycarbonate sheet. So these are as a summary, these are the viable approaches for the sustainable energy system. These are the viable approaches, that is substituting the finite energy sources, that is conventional fossil fuel. So our target should be substitute to conventional fossil fuel with the substitution of the that is by replacing with renewable energy sources, whatever is available at accessible also, and at negligible cost, and synergistic hybrid energy sources, solar wind, solar biomass, and solar geothermal. Because sometimes there is the hybrid system nowadays, that is a hybrid system is more getting attention, because this renewable energy system, renewable energy sources is uncertain in many areas. So if sometimes if solar is sufficient, so we can use the energy from the wind. Otherwise, suppose in the daytime, in solar biomass system, suppose in the daytime, if we can use the solar energy at the daytime, at night time we can use the biomass furnace or biomass gasifier. We can use a solar geothermal system. So that the multiple energy sources, combining the multiple energy sources, will make the system, make the thermal system, will make the industry can rely on the renewable energy sources. Because otherwise, because the renewable energy sources is uncertain, and also is weather dependent, is not available all the time. But for the industrial process or any other service sector, there's a 24/7 energy sources is required, energy supply is required. That's why the hybridization of energy sources is very much important. And then reducing the specific energy consumption. Energy consumption can be reduced, because in the earlier this pattern, that is the modification of the fluidization chamber. So by modifying the fluidization chamber, the energy consumption would be reduced, because of fluidization quality was increased. So because of increasing the fluidization quality, the less energy was required for fluidizing the product. And enhancing the energy utilization ratio, that means the maximum utilization of energy by reducing the wastage, by circulating this hot air or hot fluid, whatever is there. So by circulating the hot air or hot fluid, we can recirculate that is the waste heat, and we can reuse it in further process, so that the maximum utilization of energy can be achieved. then improving the energy performance of the drying system by confining the heat loss. Heat loss, it can be proper insulation and also circular strategy by reducing the heat loss from the sidewall and the exit of the system, so that the exergy performance would be increased, so the sustainability index will also be improved. Thank you.
So thank you so much, Dr. Majumdar, for this wonderful presentation, and it's really an enriching one. So let us now have a short question answer session. So from the audience, if anyone having any question, please unmute your mic and ask, or you can type in the chat box. We'll ask to our speaker. So questions, please. Questions from the audience. If there is any question you can ask directly by unmute your mic, or you can type in the chat box. If anyone having any question, kindly ask. We'll be waiting for a few minutes. If any questions comes, we'll. So from the first question from Deepak Kumar Shah. Sir, performance of solar panel on Earth and space are same?
No, sir. Because it depends on the location specific.
Okay, sir. Thank you, sir. And the next question from Archana Dwivedi. Sir, difference between utility and design patents?
Design pattern means initially we have to, first of all, for fabricating any system, we have to design by the software or anything, software. So that is the design pattern. And the utility pattern is that in utility pattern, first we have to fabricate the system, and we have to perform the experiment, and we have to get the result. So this is the difference between design and utility pattern.
Yes, sir. Thank you, sir. Thank you. So any more questions? You can ask, or you can put them in your chat box. If any questions, please ask. We'll be waiting for 2-3 minutes, and then we'll conclude the session. So in between, if anyone having any question, they can ask to our guest speaker. You can unmute your mic and ask, or you can put them in your chat box. We'll be waiting for 2-3 minutes more.
Sir, how can you optimize biomass?
We have to first of all we have to characterize the particular biomass material.
Okay, sir. Will be characterized by the help of following some protocols or what, sir?
Yeah, some protocol are there. International standard are there. We have to follow that standard and we have to characterize, and according to that we have to optimize that for particular use.
So any more questions from any more questions from audience they can ask? So one more question from Srideep Ghosh, that is there any particular organization which deals with the problem of cost optimization of global renewable energy demand?
Hello.
Yes, sir. There is a question that is there any particular organization which deals with the problem of cost optimization of global renewable energy demand?
Yeah, there are some international organizations like there, renewable energy, RENA is there, RENA is there, and other some organization also there. So there are some standard are there. Based on there are some protocol also there. Some RENA and INA.
Right, sir. Thank you, sir. And the next question from Nirmale Bhattacharya is, what is valorization?
I think it is for biomass product. So that is the before processing of biomass, that is the characterization and this pre-processing of that biomass. That is characterization.
Yes, sir. Thank you, sir. So it's almost time. So if anyone having any more questions, or we'll go to the conclusion. We're going to conclude this session. Anyone having any question, you can ask quickly, or going to end this session. Okay, sir. I think that's all for today. Thank you so much, Dr. Majumdar, sir. It was a really wonderful session and an enriching one. Thank you so much for being with us. And that brings us to the end of the day 2. Thank you, everyone, for your participation. And tomorrow we will continue the discussion on green economy and carbon reduction strategies. So again, thank you, everyone. Thank you, Majumdar, sir. And goodbye.
Thank you,
and
sir.
Thank
Thank
you,
you,
sir.
sir.
Thank you.
Sir. Thank you.
Thank you so much. Thank you, everyone. And good night, and have a very good night. Thank you.